Hi everyone! It's time to create something small in 2D again. And since simulating all devices can be very useful in games, we'll take a look at a shader that mimics the behavior of a low-quality analog screen. So let's get started. I won't waste time on a long introduction and will jump straight into coding. We'll apply this shader to an image, which I'll borrow as usual from our game Whispers of Prague. So I'll create a new scene and set up everything needed. Right-clicking on the scenes folder, create new scene. It's a 2D scene and let's call it old TV, for instance. Okay, now I will drag the usual screenshot into it. So the Sprite 2D node was automatically created right here, and in the inspector, let's expand offset and cancel centered. And let's expand transform and reset position to 0, 0. Okay, and of course we need to scroll down to the material section, create a new shader material, click it, and create a new shader, which is of type shader, mode canvas item, and the name is oldtv.gd shader, and I'll put it to the shaders folder and create, and click again to open it in the shader editor. Once again, we have some redundant functions from the template that Godot used to generate this code skeleton. Let's show more of that. So I'll delete everything so that only the fragment function remains, deleting vertex and deleting light. Okay, so let's begin. As you can probably guess, a large part of this algorithm will be based on pseudorandom noise, which we can simulate either using a noise texture or by computing it in a custom function. I've chosen a function we've already used many times before, so I'll just paste it here. The result, copied from previous shaders, looks like this. Let's expand this window and paste it right here before the fragment function. So it actually consists of two functions. The first, hash12, generates pseudorandom numbers in the range from -1 to 1. And the second one, noise, creates a smooth surface with gradual transitions across edges. So let's move on. Our effect consists of several types of distortion. Let's just collapse this window again. So it will be useful to implement each type in a separate function. Not only this will make the code more readable, but it will also give it a modular structure, making it easy to enable or disable individual components later. So first, I'll prepare the base of the fragment function right here, which is very simple this time. The final pixel color will consist of the original pixel color plus a distortion value stored in an accumulator like this. So let's delete this comment, and vec2 uv is UV. There is no shift of coordinates origin because we are just working with the whole picture. And now the accumulator, it will be vector 4. Let's call it color and start at vector 4, 0 vector, the black transparent color. And finally the output internal color is just this accumulator and the original pixel texture function applied on our texture and UV coordinates. Okay, now we can move on to programming the individual components. I'll start with the most visible one, the animated noise. So I'll insert the skeleton of the add noise function. Okay, void add noise with parameters vec2, UV coordinates of the current pixel, and in out vec4 color. Okay, Notice that the function is of a type void, meaning it has no return value. So how will the computation we're about to write affect the final result? The key is this inout keyword, which I placed before the vec4 color parameter. This allows the input parameter to also act as an output, so its value will be modified inside the fragment function. Okay, noise itself will be controlled by two uniform parameters, one for animation speed and one for intensity. So I'll add them at the beginning of the code right here. Uniform float noise speed with a hint range, and the initial value would be pretty large, 1000. And let's set the interval to, I think, 10 to 10,000, and the step can be, in this case, just one. Okay, and the second one will be the intensity or the power. Uniform float noise power with another hint range, and this time initial value can be 1 and the range is from 0 to, for instance, 5 with a step point 0, 1. Okay, and now the computation itself. Once again, this is the result of experimenting with different parameter values and various built-in functions, so I'll just write the final version. In short, it's a combination of a periodic sine function, a pseudo-random factor, and small variations depending on the coordinates of the current pixel. Actually, it is like this. Float noise x, just the fluctuations over the horizontal axis, is uv.y plus time, as we want the animated noise, times noise speed. Okay, now for the noise y variable across the vertical axis, uvx plus noise speed divided by uvy times 20. Okay, so we have some pseudo-random movement horizontally and vertically, and now let's add more fluctuations to that. Fluctuations is, and the periodic function sine of time plus 1, so we cancel out the negative values and shrink it a little bit, multiply by 0.1 and plus 0.5 to shift it on the y-axis. And finally the color modification. Color would be increased by noise power times noise function applied on vector 2, which consists of both components of our noise. So noise x, noise y, okay, and let's multiply the result by our fluctuations value. Where is it? Right here. Okay, so the function is now complete and we can use it in the fragment function. We just need to call it like this. So after a color definition, let's add noise, and the parameters are simply UV and our color accumulator. Okay, and something is going on right here. The first part of the effect is done. Notice that the grain of the distortion looks slightly different in the upper and lower parts of the image, which is meant to simulate imperfections and uneven wear of the screen. I'm not sure whether these details will stand out after YouTube compression, but when testing the shader in your own environment, they should be clearly visible. Very well, we can continue. In the second part of the effect, we'll simulate random vertical shifts of the image, which is another common flaw of CRT screens and poorly tuned analog signals. And again, we'll use two uniform parameters to control the speed and the magnitude of this offset. Okay, let me expand this window again, and let's add the mentioned uniform parameters. Uniform float, vertical speed with hint range and the initial speed, let's set it to 0.2, and the range goes from 0 to 1 with the step point 0, 1, all right. And I'll just copy and paste this line to save time and rename the second parameter to vertical shift. Otherwise, everything is the same, the hint range and the initial value 0.2. Okay, the new function will be called add movement, and this time I'll just prepare it here. Void add movement. And this time, a vector with UV coordinates will be sufficient as both input and output, since we only want to change pixel positions, not their color. The algorithm itself will combine sharp transitions between a stable state and shifted state, which we'll achieve using the step, mix, and fract functions, like this. So as I said, in out, vec2 UV, as we are supposed to change it. And now, float, let's call it shift noise, because it won't be just a simple linear shift over the vertical axis, but something more complex. And step function, which is applied on the noise function, which uses vector2 as a parameter, and the components are time times 0.5 to make it a bit slower, and 0 because we are supposed to to take the values only on one axis, and here times 0.5 plus 0.5. Okay, and I think the value is actually our vertical shift parameter. What's wrong here? I think I did something not entirely correct. Yeah, this is not supposed to be a end bracket here. Now this is correct. All right, and let's do the actual shift. So uv.y would be increased by the mix function, as we want to smoothly interpolate between the, as I said, stable state and shifted state, 0, and the second parameter is sine, again, of the time function multiplied by vertical speed, and the actual value, I mean the weight coefficient, is our shift noise variable. Okay, and this actually won't be too useful because we are making the shift sorry, I mean the value of the shift would be too high and picture would get out of the screen. So let's just use the frac function to normalize it to the UV coordinates from 0 to 1. UVY is actually fract of UVY. All right, and let's take a look at the result. Of course, we cannot see anything because the function is not used in the fragment function. Let's fix it right here under the movement, and the parameter is simply UV coordinates. And now let's wait for it. Okay, after some time, I think it should start moving in an irregular way right now. Did you see that? If not, it will definitely repeat it after several seconds, but I think it works. So another typical feature of old displays was so-called ghosting, a duplicated image showing signs of transparency and random horizontal offset. In this case as well, we'll add two uniform parameters to control it. And again, I'll expand this window and add them to the beginning. And the first one will be called ghost speed, uniform float, ghost speed with a hint range and the initial value 0.2. Okay, and the range again from 0 to 1 and 0.01 for the step. And again, we can just copy and paste this line and rename the second one to ghost power. Everything else remains the same. Very well, so I'll call the new function add ghosts, and it will be based on a slow periodic shift of the duplicated image, to which we'll give a ghostly appearance using the step function and a pseudorandom factor. Okay, let's do it right here. Prepare it, void add ghosts, and again in out vec2 uv parameter. Okay, and what I just mentioned, it should also slightly blur the edges of the duplicate. As I mentioned, the shift will be mostly horizontal, but let's add a slight vertical variation as well. Okay, so the body of the function looks like this. Float ghost noise, let's call this variable. And again, we will use the step function, and this time let's apply it on the hash12 function for simplicity. Vec2 of the parameters uvx plus sine of time, and the second component is simply uv dot y. Okay, 1, 2, and the second argument of the step function is our ghost power, and let's subtract 1. Okay, and now we need to define something called ghost cycle, because the ghost images will just go to the left and return, go to the right, and this will be repeated in the typical sine cycle. So float ghost cycle is sine function of time times ghost speed. Okay, and I think I created a half of it, so times 0.5. All right, and now the mentioned shift. First, let's shift it over the horizontal axis. This one is supposed to be more prominent, so increased by mix of 0 ghost cycle, and the parameter is ghost noise. All right, and as I said, a very slight vertical movement uv.y is increased by actually the very same, but slightly modified. The ghost cycle is multiplied by 0.2. Okay, and now we can add ghosts. We can add the add ghosts function to the fragment function. Add ghosts UV coordinates of the current pixel. Okay, and let's take a look at the result. Something is right here, but I think it might be easier to observe the ghosting if we temporarily disable the previous effect. So I'll comment out the relevant lines. Commenting out add noise and add movement. And now I see there is a movement. This is not correct, of course. Movement. Okay, and let's comment them out. Control K. And here we can see the ghost going to the, now returning from the right and going to the left. And it's also a little bit fluctuating because we applied the noise, the pseudo random factor. Okay, so it looks pretty nice, don't you think? And what's left? chromatic aberration, color distortion, and slight darkening at the edges of the image. So let's start with the first one and add a parameter for shifting the individual color channels. So the parameter number 7 will be called chromatic shift, uniform float. Chromatic shift. I'll give it a hint range and set the initial value to 0.5. It goes from 0 to 1 again, and with the 0.01 for the step. All right, and the function, let's call it add aberration. Void add aberration. All right. And it will be implemented simply. We'll slightly shift the red channel to the left and the blue channel to the right, while the green channel will stay at its position. And to avoid overly strong blurring, I'll divide the parameter value by 100. Okay, but first the parameters, and this time we need to pass the texture of our image. So the first parameter is simply sampler 2D, and let's call it text. The second one would be the coordinates of the current pixel, and finally the usual in-out vec for color. Okay, and now let's define the variable called chromatic. And as I said, it would be chromatic shift parameter divided by 100, which means multiplied by 0.01. All right, and now the mentioned shift of the color channels. So color.r, the red component, is increased by texture function applied on our texture, and UV coordinates increased by vector2 negative chromatic value and 0, of course, for the y coordinate and the red component. So what are we doing here? We just take the pixel which is shifted to the left, hence the negative chromatic value. We take its R component and add it to the R component of the current pixel. Now let's do the similar thing for the green and blue. And as I said, G and B, and the green one should stay as it is, so it's simply just UV and the green component, and finally the blue one, that should be positive chromatic value and the blue component. Okay, that's it. And now I'll add aberration function to the fragment function right here. Add aberration, and as I said, I'll pass our texture and the UV coordinates and the color accumulator. Okay, let's take a look at the result. And notice, and yeah, just to explain why I'm passing this one, the texture value, texture internal variable is defined only within the fragment function. So it wouldn't work if I just use texture inside this add aberration function. So that's why I'm passing that. All right, and we can just try the shader parameters and increase the chromatic shift. And yeah, we could see here and everywhere that the components, the color components, are more visible. Yeah, okay, let's get back to the original value. Okay, and next comes color distortion, which is also characteristic of some types of old color displays. For that, I will add another uniform parameter. Uniform float, chromatic dist for distortion with a hint range, and the initial value can be this time, I think 5. Yeah, definitely. And let's set the range to 0 to 10 with the step point 0.1. Okay, so the computation will be done in the new function called add distortion. Void add distortion. Okay, and I think the parameters are vec2 UV and in-out vec for color. Alright, and the computation itself will be based on the changes in the colors of neighboring pixels. In other words, the function dfdx, which we also know from previous tutorials. Once again, I'll apply shifts to the individual color channels of the pixel. So let's do it right here, color, and we are interested only in the RGB components. Will be increased by dfdx of the same value RGB, so it's vector 3, I mean, and it's multiplied by vector 3 and negative chromatic dist 0 and positive chromatic dist. So as I said, we are just affecting the individual color channels in the similar way as we did in the add aberration function. Okay, and I can add a call to the function in the fragment function, add the distortion, UV, and color. All right, let's show the result. Yeah, and we can see it definitely goes to some other shades of purple, violet, or combination of them. Yeah, let's get back to the original function, original value. And finally, the last element responsible for slightly darkening the edges of the screen. For this, I'll add two more uniform parameters to control the radius and intensity of the effect. A uniform float vignette radius, and with our hint range and the initial value set to 2.0, and the range goes from 0 to 10 with the step point 0, 1, and the last one, uniform float vignette power with another hint range, and this time the initial value is set to 5, and the range again goes from 0 to 10 with the with the step point 0, 1. Okay, so I'll implement the function using the equation of an ellipse whose axes intersect at the center of the image. I'll remap the UV vector into the range -1 to 1, perform the calculation, and multiply the result with the pixel color. Let's add it here, void add vignette, and the parameters, the usual ones, vec2 UV and in-out vec4 color. Okay, and now as I said, remapping the range from 0, 1 to -1 to 1. So let's call it, for example, xx or the x, and it's 2 times uvx minus 1. All right, that's the first one, and the same for the vertical one. Yy is 2 times uv dot y minus 1. All right, and now the ellipse equation float, let's call it vignette, is xx times xx plus yy times yy divided by vignette radius. All right, and finally the color change. Color is multiplied by 1 minus power function of our vignette value and to the power of vignette power. Okay, that should be everything. And we will add the function call to the fragment function. Add vignette UV color. Okay, and I think everything is done. And we can restore the commented outline so we can observe the complete effect with all its components, putting back add noise and add movement. Okay, now we should have everything we could have seen at the beginning of this video. Thank you very much for watching. I assume that in many projects it won't be necessary to implement all the types of image distortion we created today, but it's good to know they are available in the code and can be enabled or disabled from a script depending on the situation in the game. And of course, this shader can also be used for full-screen post-processing, which can be very interesting in certain gameplay scenarios. For now, take care, good luck with your projects, and I'll see you in the next video.